Welcome back to Differential Calculus. In this video, I want to introduce you to interval notation. Depending on the path that you've taken to get here, you may or may not have come across interval notation in a previous course. Whether you have or not, it's a concept that I am certain that you should be at least passingly familiar with. Really, the only new thing should be notation. Last time we were talking about sets, and we by and large looked at sets like this. Here I have the set containing the numbers 3, 7, and 12. The important thing today to think about with that is that this is a set of discrete numbers. If you think about where these are on a number line, you can find 3, you can find 7, you can find 12, you can kind of pluck those out, and everything in between is left behind. That's very rarely something that's useful in calculus. Instead, in calculus, we tend to want to look at sets of connected numbers. So instead of just 3 and just 7, we want all of the real numbers between 3 and 7. And that is what we're going to use as our definition of the interval. If I get my head out of the way, I can formally state that an interval is a connected portion of the real number line. A couple of things to stress in this definition. An interval is going to be real numbers. When I introduce interval notation in lower level courses, I generally try to talk about an interval as a way of describing a portion of a number line without having to draw the number line itself. I'll also point out here, I mentioned it earlier, but an interval is a set. We're going to use interval notation as a way of writing sets that is easier than the tools that we talked about previously for this particular type of set that is going to be so important to us throughout the course. And when we're talking about an interval, there's a couple of different ways we can classify them. The first is that some intervals are unbounded and other intervals are bounded. Qualitatively, this is fairly easy to understand. If I have an unbounded interval, maybe we'll start at 7. The interval will start at 7 and continue onward indefinitely, either above or below. There's no top of the interval. A bounded interval, by contrast, has a definite lowest point and a definite highest point. A couple of formal definitions here. A lower bound of a set is some number little m such that x is, this should be less than or equal to little m for every x in the set. And then an upper bound is some number m such that x is less than or equal to big M for every x in the set. And then we can combine those to say that a set is bounded if and only if it has both an upper bound and a lower bound. I also should mention here that a set that is bounded has infinitely many upper bounds and lower bounds. The set of between 7 and 12, this interval, I think it's fairly straightforward that I could use 7 as the lower bound, right? The set only contains things that are bigger than 7. But if you look at the definition, I could also use 3 as the lower bound here. Every number in the set is bigger than 3. There are a bunch of numbers bigger than 3 that are not in the set, but every number in the set is bigger than 3. And so sometimes it is worth talking about a least upper bound and a greatest lower bound. I've seen these abbreviated LUB and GLB. I've seen people try to pronounce them as lub and glub. I don't know if any of that is useful, but I think it's worth at least considering that there are multiple upper bounds for any set that has an upper bound. There are multiple lower bounds for any set that has a lower bound. That brings us to the second tool we have for classifying sets, which is closed and open. A set of real numbers is called closed if and only if it contains both an upper bound and a lower bound for itself. Otherwise, the set is called open. And going back to one of the sets that we've been talking about, how about the one from 7 to 12? If we're looking at all of these numbers here between 7 and 12, well, the question now becomes, is 7 itself part of the set? Is 12 itself a part of the set? If we look at, in set builder notation, the set of all x such that 7 is less than or equal to x and x is less than or equal to 12. And yes, I could have written that in a three-piece inequality. I'm specifically choosing not to here because I think it makes the point a little bit more clear. This is a closed set. There are a couple of ways to denote a closed set on a number line. One of the ones that is going to be the most useful to us is by bracketing that interval with a square bracket. A square bracket solidly hits the number and indicates clearly that that number is included. And we can use that as our tool for writing the interval notation. So the interval notation for the closed set between 7 and 12 is an open bracket, 7, 12, the closing bracket, and that is how we denote interval notation. If we wanted to insist that we do not include 7 and 12 themselves, well, then we can approach that slightly differently. The notation that we tend to favor in calculus is a parenthesis. A parenthesis nicely approaches that number on the number line, but doesn't quite get there. And so we can call that an open bracket, and that's going to be our open interval. So we have here the set of all x such that 7 is strictly less than x, and x is strictly less than 12, not including 7, not including 12. We'll write this interval notation as opening parenthesis 7, 12, closing parenthesis. And yes, that looks exactly like how you would write an ordered pair for a point in 2 dimensions. Context will almost always help you figure out which one you're supposed to be working with. Right, really quickly, I'm not going to sketch out the number lines for the other two options, but I wanted to point out that you can mix and match. If we want the set of all x such that 7 is strictly less than x and x is less than or equal to 12, then we could write that interval, opening parenthesis, 7, comma 12, closing bracket. Or if we wanted the set of all x such that 7 is less than or equal to x and x is strictly less than 12, then we could write that as opening bracket 7, comma 12, closing parenthesis. These are all perfectly valid. This first one is called the closed interval. The second one is called the open interval. And the last two, they are technically open intervals, but it's often useful to have that term open interval specifically refer to uses the parenthesis on both sides, does not include either endpoint. And so we generally just call these intervals. I might say the interval from 7 to 12, open on the left, closed on the right. Or maybe the interval open at 7, closed at 12. That's a mouthful. We don't really need to worry about it too much because these two are the ones that show up all the time. All right. That takes me back to where I started, which is the unbounded intervals. So let's start at, I guess, 7 again. And we talked about that interval that continues onward indefinitely. It can continue indefinitely to the right. It could also continue indefinitely to the left. Those are both perfectly valid things. The interval might include the finite endpoint, and it might not include the finite endpoint. In set builder notation, these are perhaps a little bit easier. This first one is the set of all x such that x is greater than or equal to 7, and that's really all we need. The second one is the set of all x such that x is strictly less than 12. But the problem here is that, well, that only gives us one endpoint, and to write interval notation, we need two endpoints. And so we will introduce a second endpoint. We're going to define this concept of infinity, which is denoted using this character. When I first was introduced to this character, my instructor taught me literally take the paper you're writing on, turn it on its side, write the number 8. That's not quite how it's supposed to work, but it's close enough for most purposes. Infinity is the bound of the entire real numbers. The entire real numbers continue onward indefinitely, but we'll pretend that we can write that in. So this first interval with x greater than or equal to 7, I can modify that to say also that x is less than infinity. X is less than infinity is nothing of note. It's not telling us anything because all real numbers are less than infinity. But by writing it in this form, now we can see that the interval notation is going to be closed bracket starting at 7, continues onward to infinity, open bracket there, the parenthesis on the right-hand side. Infinity is not a real number. You can never be equal to the real number or the number infinity. So it always has the parenthesis in interval notation. It's always open on that side. And then if infinity is the limit to the right, then I guess we can take the negative of it And we can say that x is greater than negative infinity. Again, that's not making any restriction whatsoever. All real numbers are greater than negative infinity. That's the definition of negative infinity. But that does give us the ability to write our interval notation as something that looks like that. All right, and again, the definition of infinity is that it is the upper bound of the real numbers. Negative infinity is the lower bound of the real numbers. Another nice definition is that we can write the set of all real numbers as the interval that goes from negative infinity to positive infinity. All right. So I think that's everything that we need to talk about with interval notation in and of itself. I will wrap up with one last concept here, just to point out interval notation allows us to talk about a single connected region. But it's entirely plausible that we might have two separate connected regions. And then some of the endpoints will be included, some of the endpoints will not be included. We can handle this by recognizing that this is two separate intervals. We have the interval from 3 to 5. We have the interval from 7 to 12. And we want the set that contains both of these intervals. Well, joining two sets together is the purpose of the set union operation. So that allows us to look at this set and bring it together using interval notation. At this point, the usefulness of interval notation starts to be something you can question. Is this actually better than writing things in set builder notation? Not necessarily. It is better in the sense that if you are working with interval notation, you don't want to suddenly switch. So when we're talking about sets using interval notation, we're going to tend to keep talking about sets using interval notation. If we're talking about sets using set builder notation, we're going to tend to keep talking about sets using set builder notation. Keeping that consistency is going to be more useful than anything else. When we're working with set intervals, it's almost always going to be single intervals on their own, but I wanted to mention that it can handle the other cases as well. All right, let's wrap up with one for you to try. This time I'm going to give you the set builder notation. The set of all x such that x is greater than or equal to -5 and x is less than or equal to 17. A couple of things that I want you to determine. I want you to determine if this set is bounded or unbounded. I want you to determine if this set is closed or open. I want you to determine if this set is an interval. If it is an interval, I want you to write it in interval notation. And I want you to graph it on a number line. I will mention that that last step is probably your place to start. Graph this interval on a number line, make sure that it makes sense, and then answering the rest of the questions should fall into place from there. Take a few minutes, see where you can get to with this problem, and I'll see you in the next video.